selecting a motor, you really want to know the torque and the RPMs. Decrease the speed by a ratio of 10 to 1, the torque also goes up by 10 to 1. Open loop is where there is no encoder feeding back to your controller the position. If you're going to run this thing 24/7 and you want to run it at some optimal speed, then a VFD on an AC motor is a much better choice. So on a recent project, we had 2 conveyors that run at a constant speed, but the speed was needed to be adjustable, so they had VFDs on them. And then we had 7 axes of linear motion where we needed to position accurately, and those motors were servo motors. And we also needed relative speed. Steppers could have done the job, but the machine would have been much slower because the RPMs we needed was quite high. Also, in that same thing, there was a fan motor, and the fan motor for cooling the cabinet was a brushless DC motor that ran on 24 volts DC. So, you know, a lot of motors in one little machine.
Gary, can you explain how heat can affect motor selection?
Heat is a factor, but pretty much the amount of heat that a motor generates is equal to the power of the motor. And so that means that for equal amounts of power, the motors pretty much generate the same amount of heat. So if you need a certain amount of power, the motor is not going to be the type of motor is not going to be much of a factor. Some motors are more efficient. That is probably the biggest factor, is the efficiency difference. In some of your speed controlled motors that are permanent magnet servo type motors, they can have very high efficiencies compared to an AC induction motor. AC induction motors you see everywhere in industry due to the fact that they're pretty much bulletproof. You can do almost anything to them without damaging them. They'll take overloads that are 400%, and you know, and they hold up really well. And they're also like the cheapest type of motor because there's not a lot in them. So yeah, heat's a consideration. Oh, and so let's bring up the heat factor a little more. Just yesterday, we had a motor in here that we were checking to see if it was working okay. And a comment was made, wow, the motor gets really hot. And I said, well, what's really hot? Turns out that if you look at most motors, the nameplate will tell you a temperature rise. And the temperature rise for induction motors, at least, is typically 40 degrees C. You say, wow, that's pretty warm. Yeah, except that it's rise. In other words, it's how hot the motor can get above the ambient temperature. So it's 40 C added on to 20 C or 25 C that is the environment. So that's way too hot to hold your hand on. So your hand being able to tell that the motor is too hot is not a good judge, because you can only handle about 130 degrees Fahrenheit, and that motor can run at 190 and be perfectly fine. Now, the other thing interesting about that was this particular fan was driving a fan, and the motor was rated as air over. Air over meaning it was intended to be in an airstream to cool it. And that airstream was provided by the fan. They mounted the motor in part of the airstream. When the cover was on, the motor didn't get very warm. You could hold your hand on it. But when the cover was off, it got up to that high temperature. Now, of course, the heat is going into the load. And talking about heat, where does the energy from a motor go? Ultimately, all of the energy used by motor winds up as heat in the environment. So I had a task of choosing a cooler to cool down a process, and the process involved a lot of pumps. And so I calculated how much the liquid was going to rise in temperature simply by based on adding up all the kilowatts of energy that the pumps were producing. And as it turned out, the operating temperature of the system was very close to the ambient temperature, and so I didn't have to account for the temperature of the water getting warm due to the room. And so we worked it out, and then we bought a cooler, and the cooler was perfectly matched to the task. So when you put a machine in a room, if you have a bunch of motors, you may overwhelm the cooling system in the room. That's that happens a lot.
What considerations should there be for a special application like powering an air compressor?
Air compressors. Some loads are very hard starting, and an air compressor happens to be one of them, usually because they're trying to start against the load of the air that's already in the tank. And they do put unloaders on them, and that will let the air just blow out while the motor's getting up to speed, and then it closes. But there's another interesting factor with air compressors, and that is every manufacturer pretty much overloads the motor intentionally in their gear when they gear it. And the reason is that they typically run on a pressure switch that turns it off when the tank reaches pressure. So the pressure goes up, and as the pressure is going up, the load on the motor is going up. If you're using hardly any air, it will go up to the pressure switch and turn off, in which case the overload was a very short period of time. If you're using lots of air, it will never get up to the pressure, and therefore it will never be overloaded. So they intentionally overload the motor to get more air from a given size motor. Only gotcha is that if you're the guy wiring the motor and it says that it draws 10 amps, and so the motor's rated 10 amps and you put a breaker on it, you may have trouble with the circuit breaker tripping due to the fact that during that short period of time, the motor could pull 15 amps, but you didn't oversize the breaker to take up the difference. Any other questions?